Hello ladies and gentlemen, this is George Kamiti. Welcome back to our channel. Today we are solving this question that says this. The figure below shows a steel bar of cross-sectional area 250 square millimeters held firmly by the end supports. So this steel bar is held firmly at L and M. That's why we got the supports that will prevent this steel bar from extending in any given direction. It is loaded by an axial force of 25 kilonewtons. So we got a load of 25 kilonewtons that is subjected at this point here. We are expected to do the following to determine the reactions at L and M. That is RL and RM. Then we are also supposed to determine the extension of the left portion, that is portion A. Now we know that the Young's modulus of elasticity is given by the ratio of stress to strain. We also know that stress is given by load divided by cross-sectional area, and strain on the other hand is given by the ratio of changing length divided by the original length. So when we substitute the value of stress here and strain, we are going to have a stress load over area divided by strain changing length over the original length to give us load times length divided by cross-sectional area times the change in length. That is the reciprocal of strain. So the Young's modulus of elasticity will be given by load times length divided by cross-sectional area times changing length. We need to make a change in length the subject, and in this case, the change in length will be given by load times length divided by cross-sectional area times the Young's modulus of elasticity. Now, we are being asked to determine the reactions at L and M, and we need to know this. When the section or when the portion A is subjected to tensile force, since it cannot extend beyond this support, since it is firmly fixed, it will transfer that extension in form of a force towards this portion B, and that means that the portion B, when it is subjected to a tensile load towards this direction, it will contract since it cannot extend beyond this support. It is firmly fixed. So we can say this. The extension of the portion B, let's call it portion A, sorry. The extension of the portion A, since this is the portion that has been subjected to tensile force, is equivalent to the contraction of the portion B. Contraction of the portion B. So that is what is going to happen. Now, applying this changing length, that is extension is changing length, contraction is also changing length. So we can say that the load subjected to portion A times the length of the portion A divided by cross-sectional area of the steel bar times the Young's modulus of elasticity of steel is equivalent to the load subjected on the portion B times the length of the portion B divided by cross-sectional area of the steel bar times the Young's modulus of elasticity of steel. Now, this load PA and PB are the reactions RL and RM respectively. So we are going to have this relation. The reaction L times the length of the portion A, which is 0.25 meters, divided by cross-sectional area of the steel bar times the Young's modulus of elasticity of steel is equals PB, which is reaction at M, times the length of the section B or the portion B, which is 0.6 meters, Divide this by cross-sectional area of the steel bar times the Young's modulus of elasticity. Now, since A and E are common, definitely they are going to cancel each other. So we are going to remain with the reaction at L times 0.25 is equal to the reaction M times 0.6. Let's make our L the subject, and in this case we are going to divide both sides by 0.5. 0.25, I mean. So divide both sides by 0.25. And in this case, the reaction at L will be given by 0.6 divided by 0.5. That happens to be 2.4. So we are going to have 2.4 Rm. Let's call that equation 1. Very good. So that is our equation 1. Now, we also need to know that since this steel bar is in equilibrium, the way it is loaded, when you add the reaction at M plus the reaction at L, you are going to get 25 kilonewtons. Remember, the forces that act in the same direction, we are supposed to add them to get the total load. But this one is acting in the opposite direction of these two reactions. So we are going to say this: the reaction at L plus the reaction at M will give you 25 kilonewtons, the resultant force. Now we have RL being 2.4 Rm. So let's substitute this one here. And this is going to give us 2.4 Rm plus Rm being equal to 25 kilonewtons. 2.4 plus 1, that happens to be 3.4 Rm. 3.4 Rm is equals to 25. To get the value of Rm, divide both sides by 3.4, divide this side by 3.4. And this is going to give us a reaction at M of 7.353 kilonewtons. So that is the reaction at M. Now, after getting the reaction at M, we can get the reaction at L by using this equation 1. And this is going to be, the reaction at L is going to be 2.4 times Rm. And Rm in this case is 7.353 kilonewtons. So the reaction at L is going to be 17.647 kilonewtons. So, ladies and gentlemen, that is the reaction at L, and this is the reaction at M. So we have answered part 1 of the question. Part 2 of the question is asking that we calculate the extension of the left portion. This is the portion A. Now, when you come here, we will find this relation that the reaction at L times its length divided by AE will give you the extension. It will give you the extension of the portion A. So in this case, we are going to say this, part 2 of the question, the change in length, that is the extension of the portion A, will be given by reaction at L times the length of the portion A divided by cross-sectional area of this steel bar times the Young's modulus of elasticity of steel. So this is going to be reaction at L, that is 17.647. That is kilonewtons. We are going to convert it to newtons. We multiply it by 1,000, multiplied by the length of the portion A, that is 0.25 meters. 0.25 meters. We divide this by the cross-sectional area of the steel bar, that is 250 square millimeters. We need to convert that to square meter. That is by dividing 250 by 1,000,000, because 1 square meter is equivalent to a million square millimeters. So in this case, we are going to divide 200 by 1 million, and that is going to be 200 times 10 raised to the power of negative 6, multiplied by the Young's modulus of elasticity of steel, 200 giganewtons per square meter. We convert to newtons per square meter. So that is going to be 200 times 10 raised to the power of 9, since giganewton is equivalent to 1 billion newtons, and a billion 9 zeros. So in this case, the change in length in portion A will be equivalent to 8.824 times 10 raised to the power of negative 5 meters. So that is when you multiply all this, divide by that. When we convert these to millimeters, we are going to multiply by 1,000, since 1 meter is equivalent to 1,000 millimeters. And in this case, the change in length will be equivalent to 0.08824 millimeters. So this is the extension in the left portion. So we have answered both questions, and we are through with that. Problem. So thank you very much for watching our content. If you are here to subscribe, don't forget to do so. Thank you. Let's meet in yet another.